Okay, Unit 6, Chemical Equations. Now, this is the way we represent a chemical equation. We have reactants, which is what we start with, and then the arrow indicates progression or the formation of products. Now, the arrow can be referred to in many different ways. There's the process of going from reactants to products. We could say that the reactants yield the products or produces, forms, makes the products, whatever verb you want to use. Let's look at an example, the cellular respiration. This is what takes place when you breathe. The sugar, your blood sugar, and oxygen combine together or react together to form carbon dioxide water, and it also produces energy, and it's the energy that gives you life. Now, in this reaction, this is glucose and oxygen. Those are our reactants, and carbon dioxide and water are our products. Now, you're already familiar with subscripts. Subscripts are the little numbers that we write below each of the elements to tell us how many of those elements are in the compound. What's new, and what our focus is here, are the coefficients, which tell us how many of a particular atom or molecule or compound that we have. So the 6 here indicates that we have 6 oxygen molecules. Over here, we have 6 carbon dioxide molecules and 6 water molecules. And the reason for those coefficients is so that we have exactly the same number of each type of atom on each side. If we were to look at all of the carbons on the reactant side, we have 6 of them. Over on the product side, we have 6 of them. We have 12 hydrogen. We have 6 times 2, 12 hydrogens. We have 6 times 2 is 12 oxygens here, plus 6. That gives us a total of 18 oxygens on the product side. And if we look on the reactant side, we have 6 here, plus 6 times 2 is 12. So we also have 18 oxygen atoms on the reactant side. So that's the name of the game, to write a chemical equation that represent the reactants, those substances that combine together to form new products, and to write coefficients such that we have the exact same number of each type of atom on each side. A chemical reaction represents a chemical change, involves the breaking and forming of chemical bonds. So in your reactant, bonds are broken, your products or bonds are formed. So you have new material, new substances. We represent chemical reactions by writing balanced chemical equations. So let's look at an example, the combustion of methane, combustion burning. So methane CH4, oxygen O2, produces carbon dioxide and water. Okay, so let's draw a little line here to separate the reactants from the products. Now I'm going to use structural formulas so we can better see what the reactants and products are. So this is methane, CH4, 1 carbon, 4 hydrogens, O2, 2 oxygens, double bonded, carbon dioxide, and water. Okay, now in balancing a chemical equation, we need to have the same number of atoms on each side. So let's just take a look at one of the atoms, or look at atoms one at a time. So we have 1 carbon here. So over on the product side, we need 1 carbon, which is what we have. That's the only place we have it right there. For hydrogen, we have 1, 2, 3, 4 in methane. So over on the product side, we need to have 4 hydrogens, but we don't. Water only has 2 hydrogens. So what we'll need is to have 1 more water molecule. And we represent the fact that we have 2 water molecules by using a coefficient out in front. Now note that we can't change the chemical formula. I can't just make this C4O because that's not water. Water is H2O. So the only thing that you have control over is the coefficients. The formulas are locked in. You can't change that. Okay, now once I do that, you can see that that means I have 2 oxygens here, and then over here I have 2 oxygens. So over on the product side, I have a total of 1, 2, 3, 4 oxygens. So over on the reactant side, I need to have 4 oxygens. But as it is, I only have 2 oxygens. So that means I'm going to have another O2. And I can represent that by putting a coefficient of 2. So that is a balanced chemical equation. And so that's our goal here. Okay, one more thing about balanced equations. They obey the law of conservation of mass. The law of conservation of mass states that matter can neither be created nor destroyed in any physical or chemical process. Specifically for our purpose here, the mass of the reactants has to equal the mass of the products. Specifically, the total reactant atoms must equal the total product atoms. We have to account for every single one. Okay, now this is a little animation. I'll talk about this at the end of the slideshow here. This is from a website called PhET, PhET Simulations. And what they're giving you here is a chemical equation, and what you'll be able to do is to change the coefficients. And then you can see that you have a little balance up here that represents the number of nitrogens that you have as a reactant and a product, number of hydrogens you have as a reactant and a product. So it's just looking at the two atoms that are involved in this reaction one at a time. Okay, now this is, I made a little movie of this. So let me I've now made this, so I have two nitrogens here. So you can see up here, on the reactant side, I have two nitrogens. So in order to balance, I need to have two nitrogens on this side. So if I go over here and make this a 2, that'll give me 2 nitrogens. Okay, so now the nitrogens are balanced. But when I put in the 2 ammonias, that means that I have a total of 6 hydrogens. 2 times 3 is 6. So you can see those 6 hydrogens. So over on our balance here, you can see I have 6 hydrogens on the product side. We need to have 6 hydrogens on the reactant side to balance. So over here, I can change the amount of hydrogen so that I have the same number of hydrogens on either side. So the same number of nitrogens on both sides, same number of hydrogens on both sides. So this is our balanced chemical equation. So that's the whole game here, is to what are the coefficients? Write the correct formulas and then put in the correct coefficients. Okay, now there's some hints to help you do this. So let me walk you through. There's 5 hints, and these are pretty helpful. First, balance elements or polyatomic ions one at a time by adding coefficients. Now that's what I've already been doing, but let's look at it again. You'll often need to be able to write the chemical formula yourself. So hydrogen and chlorine and hydrochloric acid, you should be able to write the correct chemical formulas. So this is a case where let's have you stop the video, see if you can do that. Can you write the correct formulas for these reactants and products? Give it a shot. All right, now hydrogen and chlorine, hopefully you remember, are 2 of the 7 diatomic elements. So hydrogen is H2, chlorine is Cl2. Just like water is H2O. If I say chlorine, it's Cl2. Hydrogen, H2. Hydrochloric acid is HCl. Okay, now we need to balance the equation. Then you see you have 2 hydrogens here, so I need to have 2 hydrogens here, so I can get that by putting a 2 out in front. Now when I do that, that also means I have 2 chlorines, which is good, because that's what I need. I need 2 chlorines. So this is a balanced chemical equation. Okay, so that one was pretty easy. And by the way, sometimes the chemical equations don't need a coefficient, just the formulas themselves balance it. But usually you need to have a number. And one other thing, the numbers are always small whole numbers. Occasionally you'll get like a 15 or a 12 or something like that, but by far they're almost always a 1, 2, 3, or 4. Okay, treat polyatomic ions as blocks. So sodium sulfate reacts with aluminum nitrate to form sodium nitrate and aluminum sulfate. So again, why don't you pause the video, see if you can correctly write those formulas. Okay, sodium sulfate, aluminum nitrate, sodium nitrate, and aluminum sulfate. Right, now, the hint here is telling us to pay attention to polyatomic ions that remain intact. So you can see you have sulfate here, and you have sulfate here. You have nitrate here, and you have nitrate here. So there's no reason to count them individually, like 1 nitrogen, 3 oxygens. We can treat them as one unit. So we have 1 sulfate, 3 sulfates. We have 3 nitrates, 1 nitrate. Okay, so let's balance the sulfates first. So 3 sulfates. So over here, to have 3 sulfates, I would need to have a 3 as a coefficient. Now that's going to give me a total of 6 sodiums. So over here, to balance the sodiums, I would need to put in a 6, which is going to give me a total of 6 nitrates. Over here, I only have 3 nitrates, so I'm going to need to put a 2 in front here to balance the nitrates. And that means I'll have 2 aluminums, which is good because that's what I need here, 2 aluminums. So that is a balanced chemical equation. Again, the hint here, if you see a polyatomic ion, treat it as one thing, one unit. Makes it much, much easier. You could break it apart to, the 1 sulfur, 4 oxygens. It's just much more difficult. 3, start with elements that are present in the least number of substances. So when we look at this reaction, see that you have hydrogen here, here, and here. And oxygen, you have here, here, and here. Whereas nitrogen only appears in 2 substances, and carbon only appears in 2 substances. So it's best if you start with one of those, nitrogen or carbon. So let's look at let's try the nitrogen first. You have 2 nitrogens here. So if I put a 2 here, that'll give me 2 nitrogens. I have 1 carbon here, 1 carbon here, a total of 3 oxygens, 3 oxygens, a total of 8 hydrogens. 3 times 2 is 6 hydrogens here, 2 hydrogens here. So that is a balanced chemical equation. Next, check that all elements are balanced using the smallest coefficients. So in this reaction, you might think that it's balanced, and technically it is, but we can divide everything by 2. Just like an algebraic equation, we can reduce this. So if I divide everything by 2, I'll have the correct balanced chemical equation. So you wouldn't want to argue that that's balanced because it's not reduced. It needs to be reduced. And last, if all elements balance except a diatomic element, double the coefficients used. Okay, so let's look at an example. Okay, so this is pentane. This is the combustion of pentane producing carbon dioxide and water again. So let's balance this. You have 5 carbons. So over here, I need 5 carbons. You have 10 hydrogens. So over here, I need 10 hydrogens. But then when you go to balance the oxygens, there's a little bit of a problem. The 5 carbon dioxides gives you 10 oxygens, and the 5 waters gives you 5 oxygens, which means on the product side, you have a total of 15. Well, there's no number you can put in front of the O2 to give us 15. We want whole numbers. So the hint here is if we double all the coefficients, when we find that as a problem, double all the coefficients. So the pentane here has unwritten 1. We can make that a 2. We can change the carbon dioxide to 10 and change the water to 10. So now we can balance the oxygen. Now we have a total of 20 oxygens from the carbon dioxide and 10 oxygens from the water, which means that we have a total of 30 oxygens. So on the oxygen side, if we put a 15, that would give us 30 oxygens. And you'd want to rewrite that, and that would be your balanced chemical equation. All right, now last, the PhET simulation, there's a link for it that I gave you. If you go to the PhET website, it's pretty cool. The introduction, you can play around with that, but let's look at the game. Okay, there's different levels, so what you would want to do is start off easy and get progressively more difficult. I'll start off easy. Okay, so now what I always do is always make it a 1, all the coefficients 1, because it has to be at least 1. Okay, now I have 1 phosphorus here, 1 phosphorus here, so the phosphorus are balanced. I have 5 chlorines here, I have 3 chlorines here, and 2 chlorines here. So this is a case where you don't need any other coefficients. Everything is already balanced. Now I can check that, and it's good. Let me try another one. This one I'll deliberately get wrong. So let's just say I'm out of my mind here. Okay, when I go to check it, it'll tell me that it's not correct. Why? And it uses those little balances so you can kind of see why it's lopsided. And then you can try it again. All right, so that's kind of a fun thing to practice before you get going on the homework.